Hello, welcome. My name's Gavin Nielsen, and this is the first in a series of 12 lectures on modeling, simulation, analysis, and analysis using MATLAB and Simulink. This is the first one, and we're going to cover an introduction to the talk, a little bit of orientation inside MATLAB, and hopefully first blood project to try to get dirty. So let's keep rolling. A little bit about myself. I went to school at Chico, got a bachelor's in computer engineering and a master's in electrical. I've done a lot of different consulting gigs and, mechanical engineering and electrical engineering and some computer science, software development type of stuff. Got to be a basketball coach for a while, worked in Army research for a little while, doing helicopter development stuff. A little bit of entrepreneurial work and starting some companies, which has been fun. And currently I'm developing some companies in ag tech and trying to push the state of the art there forward and make food cheaper to buy and farmers able to continue to live and so on. That's a little bit about me. Okay, so why am I here? It's good for you to understand. Firstly, I'm here to encourage students, all kinds of students, that whatever they are studying, they should keep studying, and we can use all different kinds in not only in engineering but in all the different disciplines. Modeling, as we'll talk about, modeling, simulation, analysis, it's pretty much everywhere. So welcome. I also want to talk to you a little bit about what happens after school, not like after school hours, but I mean after you're out of school. Talk about some practical ways that things are done, because it doesn't always mirror what's taught as the classical way. It's not always the best way to learn. So it's useful that you know what's going to happen in a lot of times once you get out. Also, to begin the conversation with your brain on this stuff, because modeling, simulation, analysis, like I said, is just everywhere. And the sooner you start engaging with it, the deeper you'll understand it, and the more you'll be able to use it. I would like to help you build some skills that are marketable and maybe make it easier for you to get a job, hopefully. I'd like to give you some tools to make awesome projects with while you're at school, because you need something to brag about, in those job interviews. You want to have something cool to say, and plus you want to have fun while you're in school. So it's good to have the tools to make it happen. And then obviously once you get out, projects just get bigger and cooler, and so you still need cool tools to do that with. So that's a little bit why I'm here. So what is this seminar about? Well, let's talk about what it is about and what it isn't about. A couple, just in rough strokes, it's about getting dirty with imperfect descriptions of your interests to learn more about them. That's kind of what modeling and simulation analysis is. It's taking a shot. Let's try something. Let's take a stab at it. It's about understanding the trade-offs between accuracy, practicality, and necessity in modeling, because that's what separates really good modelers from people that just model and waste a lot of time, because you can waste years of your life working on something that really isn't that helpful when you don't understand what those trade-offs are. And also, it's about getting a foothold in the world of system modeling and simulation so that you can continue and have some kind of grounding and go pursue whatever branch. It's such a massive world. There's so many different types of models and simulation techniques, environments, and so on, different ways, approaches, and then a myriad of things to do, things to simulate. So hopefully this will give you a foothold. Okay, let's talk about a few things that we're going to refer to, but they're not the main aims of this. linear algebra. We're going to spend a lot of our time in MATLAB, which stands for Matrix Laboratory. So you might assume that we're going to be doing a lot of linear algebra. That's not really the case. There's plenty of material out on linear algebra, and you can buy a book or watch a YouTube video about it or something, but that's not what this is about. Also, it's not specifically about mathematical modeling. As a formalized, we're not talking about the math as much as the concept of modeling. And of course we're going to be using math because that's kind of how you do it. But where we don't need it, we're not going to use it. And that's not to say that you shouldn't. That's to say that when it comes to it, we're trying to get something done. You don't always symbolically model everything. You don't always start from first principles. So mathematical modeling may be helpful. It generally is, and you generally use math to describe things. But this course is not about that. So I encourage you to pursue all these other topics. It's just not going to be here. Control theory. Anytime you talk about system level processes, there's almost always some control theory aspects. We're going to, by and large, ignore those, and I'll encourage you to go pursue that. It's the most exciting dry topic you'll ever come across, I think, and the more you get into it, the cooler it gets. But it just is a very deep topic. So we can't help ourselves but do a little bit of programming and algorithms in this seminar, but we're not going to be focused on that. Really, we're trying to stay focused on, like I said, modeling and simulation. Same with circuits. That's a useful thing to get a sense of how to model, but we're not going to focus on the theory there. And finally, machine design. Towards the end of this, we're going to talk a bit about three-dimensional modeling, how to connect that into other types of models, but we're not going to focus there. Okay, so all that said, what sorts of things will it cover? All right, well, we're going to go over the basics of MATLAB. That's a product by the MathWorks, and we're going to talk about some language fundamentals. We're going to get into algorithms a little bit. We're going to spend some time on visualizations because that's super important. Of course, functions and interfaces implicitly. We're going to talk about Simulink, which is another MathWorks product. It's sort of the graphical block diagram tool, and we're going to talk about its language fundamentals and some different things. State machine modeling using Stateflow, and physical models using Simscape. Then we'll spend a couple of days, a couple of sessions on SolidWorks basics, and that's 3D modeling, so geometric type of things, and do a little simple feature creation, a little bit of simple assembly, and if we have time, we'll do a little bit of finite element analysis, FEA. So concepts, generally speaking, we're going to, like I've been hammering on here, we're going to focus on modeling, simulation, analysis. But some of these things that I'd like to bring along are small scale and large scale algorithm design. Again, not formally, but conceptually. How do we approach this, or what does it mean? Talk about interfacing because that's how we get anything done. We've got to make efficient interfaces. And finally, being fearless about trial and error. We got to go try stuff. And it's usually time that's against us, so the longer we delay, the longer it takes to actually get something done. So these are the topics we're going to cover. So the agenda for the semester, we're going to do it in 4 phases. The first part's going to be tooling and basics. We'll cover, like I mentioned here, the basic things, tours, and so on. Then we're going to talk about modeling algorithms. Now, some people might look at this and say, what do you mean modeling algorithms? Why don't we just talk about algorithms? But as you'll see, creating models of algorithms is actually more efficient. And once you understand what the algorithm does and what you want it to do, which we'll go through, these present some very flexible ways to wield that. And then phase 3, we'll talk about modeling circuits, and we'll spend just a couple of days on that. Different types of circuits and how to model those inside Simulink. And then finally, phase 4, we'll do a little modeling in 3D, and we'll pull that back in and connect it with everything else. So that's our plan. So modeling and simulation is everywhere, and some of this you might easily expect. You know, the formal sciences like math, formal logic, chemistry, physics or science, the physical sciences, and engineering, and so on. You'd expect modeling and simulation. Others make sense, but you may not expect them, like biology and genetics. And some are just surprising that there's modeling and simulation going on. I would say they might be surprising, but criminology, demography, law, linguistics, psychology, sociology, people are building models and using simulation and really harnessing that power across all disciplines. So these are just some things that you may not have thought of. You know, biomedical engineering, environmental science, urban planning, pretty much anything you can name, you can use modeling and simulation to help improve. So I hope that you are encouraged by this long list, and this is not exhaustive by any stretch, just to open your mind a little bit to how broad modeling and simulation is. Okay, so from time to time we're going to stop talking and get dirty here. And what I mean by that is we're going to hop into MATLAB and just not talk too long. Okay, so I'm going to start a new script. This is the MATLAB IDE, and I'm going to go down here to the command prompt and say CLC, which is clear command window, and I'm going to write a few messages in this script. Why am I here today? If I run that, x equals 3, keep running it, okay, and y equals 3 times x, y equals 9, okay. So this is just a couple quick things. We saw how to display DISP, and here we sent it some text. We can also send it display y, and it'll display the value of y. And let's do one more quick thing before we get back. This is the value of y. Number to string y. And we'll talk about the syntax, what this all means. So here it outputs this, and in fact, let's start this off with a CLC at the beginning so that we clear the command window. Why are we here today? X equals 3, y equals 9. This is the value of y, 9. We can see some of the things that made this work. So this is your first super quick look at a MATLAB script, and this is just so that we keep our feet on the ground and don't get too heady in our theoretical discussions. So we're going to switch back now. We're about 15 minutes in, and we're going to get back to the discussion on the introduction of philosophy to modeling. So the question here is, why ask why? You know, why are we discussing what modeling is? Why not just go do it? Well, we'll see. What is a model? Maybe pause the video if you would and think about it for a sec, but we'll hop into it here. In our context, it's a system or thing used as an example to follow or imitate. So that's actually kind of odd, because we can either follow it or imitate it. So which way is it? Is it the thing that we're mimicking, or is it the mimicry itself? This is something useful to think about. what does a model mean? Is it the model home that everything is based off of, or is a model of the home that's a representation of the home? And another way to put this is, which one is the model? Is it the block A or block B? If B approximates A, is B based on the model A, or is B a model of A? And the answer, as you might guess, is both. Modeling is a very strange thing in that way that it can be both source and destination, and typically you talk about one at a time just because it gets confusing. But a lot of what we're going to do for these sessions is making it B. We're going to approximate something else, and making it the thing that's going to be followed. A is really a design type of action. So what we're going to be spending most of our time with is figuring out how to imitate things. Okay, so what does it mean to simulate then? Okay, simulate's a verb. It means to imitate the appearance or character of. Well, I guess that sounds a heck of a lot like what modeling was. To imitate, right? So, are they the same thing? No, they're not. The model, so we're going to separate them here. The model is the declaration of the relationships. So it's like the definition or something you would express. The simulation is the execution of the relationships. I want to point out the fact that simulate is a verb. And you might come back to me and say, well, model can be a verb too. But my point here is that simulation in our context is the execution of those relationships. Okay, and finally, analysis. Let's just talk about briefly what analysis means in our context. The detailed examination of the elements or structure of something, typically as a basis for discussion or interpretation, or the process of separating something into its constituent elements. Okay, so we have modeling. It's a declaration or definition of relationships. We see that simulation is the execution or the evaluation of those relationships. What else is there left to do? When we think about analysis, we almost want to say both of those things. Well, aren't we analyzing it by declaring it, or aren't we analyzing those relationships by evaluating it? Well, I would argue that analysis is the examination of or the reasoning about the relationships based on what simulation results we have. And we can talk more in detail about that later, and how some of these details get ironed out. But this is the structure of how we're going to be talking about these three words: modeling, simulation, and analysis. So here's the cycle. We model. The model takes in an analysis reasoning about relationships and defines them. Simulation takes in a model's definition of relationships and evaluates them. And an analysis takes in the simulation's results and reasons with them. So this is a symbiotic type relationship, and we can see that this doesn't really have a head or a tail. So you might start with the simulation. In a real sense, the simulation might be an experiment, and if it's not a virtual simulation, it might be a physical simulation of what's going on. And we need to start with data, or maybe we start with the reasoning and build a model and then simulate. Or perhaps we don't know very much, so we just start with anything, with a model, make a definition, simulate, and then use that to create data. So there's not really a start or an end, but I would say in general, usually it happens that you analyze something or you reason about it to make a model, and then you simulate it and analyze that data. Okay, So that seems straightforward, but what's the big challenge? What's the big deal? The big challenge is something called Bonini's paradox. And there's different people say it differently, but one way to say it is, as a model of a complex system becomes more complete, it becomes less understandable. And the more modeling you do, the more you'll realize this to be true. As you elaborate something, you start to notice a trade-off. Another way to say that is, everything simple is false, everything which is complex is unusable. And this seems a little stark because, well, goodness, how do we build something that is worth building? If everything simple is false and everything which is complex is unusable. Okay, so the answer is we find a balance. And so if we look on the left, we're talking about the continuum of model fidelity, and on the left we have very low fidelity, simple models. They tend to be less accurate, very quickly simulated, generate very small data sets. Those data sets are very easy to analyze, but typically yields little to zero insight because it's so simple. And then on the opposite extreme, on the right-hand side, when the model becomes extremely high fidelity, it becomes extremely complicated. It also becomes very, very accurate, but the simulation time grinds to a very slow time. Simulation becomes very, very slow. It generates massive data sets, and those are typically difficult to analyze. So theoretically, you have infinite insight with that extreme, but there's a reasonable range, and that's what we're interested in. And that's where we get the model to the minimum complexity we need, to the necessary fidelity we need it to be. Fidelity is faithfulness. So how faithful is it to real life? We don't have to make it exactly like real life. Just necessary fidelity. We don't have to have infinite accuracy, we just need practical accuracy. Are we good to 3 decimal places? Okay, that's probably alright. Yeah, I'm just saying, for some particular project, maybe 3 decimal places is good. What's a reasonable simulation time? Is it a few seconds, a few minutes, a few hours, a few days? It's hard to tell from the outside of a project, but that might be reasonable, or maybe it's a huge thing, and reasonable means a couple months. I don't know. Sometimes you need to run 1 million simulations, so a reasonable simulation time for one is got to be less than a second, maybe. You need to have a manageable data set because we don't have all the memory in the world. It's getting cheaper and cheaper, but it's amazing how much data you can generate from a simulation. And we've got to be capable of analyzing the data. The more complex the model, the harder it is to analyze, the more complicated that analysis becomes. And what insight, this is really a driving thing. What insight are we looking for? Why are we even doing this? We should build this to get to that necessary fidelity and to achieve the needed insight that we're looking for. So this is what's called Bonini's paradox. Okay, and the two factions are complexity and simplicity. And so on the complexity side, I'll read this quick quote. I claim that many patterns of nature are so irregular and fragmented that, compared with Euclid, a term used in this work to denote all of standard geometry, nature exhibits not simply a higher degree, but an altogether different level of complexity. The existence of these patterns challenges us to study these forms that Euclid leaves aside as being formless, to investigate the morphology of the amorphous. And that's Benoit Mandelbrot, who you might recognize his name from the Mandelbrot fractal, or the Mandelbrot set. He did a lot of research. He was a mathematician, did a lot of research with fractals. So, and what he's kind of getting at there is that certain complexities are irreducible. They don't project well into a simpler form. As he said, not simply a higher degree, but an altogether different level. And what the trade-off is, we'll lose insight if we simply ignore some effects. And so that's the space that we're working in as modelers, to try to figure out what insight do we need, what can we ignore, and what do we have to capture? Which effects do we want to capture? We're not going to talk about the technical details here, but a lot of times, or most times, when you're learning about analysis of particular systems, dynamic systems in particular, you tend to talk about the linear. You tend to talk about linear systems because they're easier to analyze. And I'm not saying that's a bad idea at all. I think it's a great idea. But you should be aware that nothing's actually linear. It's a projection or an approximation of something. And so hopefully it's good enough, because if it's far simpler. If it's not, you need to realize what you're not capturing by making it linear. And lastly here, certain useful effects are only observable at higher fidelities. So like the memristor, if you Google this, go to, type in memristor in Google, and you can see that's a fourth foundational circuit element, along with resistors, capacitors, and inductors. But we couldn't even observe this until we got to the nanoscale. And even then, it took us some time to, we discovered it on accident. It was predicted 30 years or so before it was actually observed. So that's one of those effects that if we didn't have the higher fidelity of those particular experiments, we would never have seen the effect. On the flip side of that, we have simplicity. And we note that balance is best. Simplicity and balance are best, but they're not the only challenge. So Einstein said everything should be made as simple as possible, but not simpler. And what he's saying there is you need to set a standard for how simple you can make it, but not go lower than that, not simpler. So when you get simpler than you should, you start throwing things away that are important. Another interesting quote along these lines is Occam's razor, and one rendering of that is, among competing hypotheses, the one with the fewest assumptions should be selected. And it's really something more dealt with in philosophy and formal logic. But here we can see it's also related. We want to not have too many dependencies, not too many hypotheses. We want to try to get down to the simplest form we can. And I kind of like this quote by Thor Heyerdahl, I think I'm saying his name right. Progress is man's ability to complicate simplicity. You may disagree or agree with that, but I think it's interesting to contemplate. I won't comment on it further. But fundamentally, we may lack the data to analyze. Okay. Sorry about that. We may lack the data to analyze. We may lack the time to simulate. Or we may lack the insight to model. These are kind of the fundamental problems. Practically, here's some of the things that usually get in the way. We may not have the money to do any of this stuff. We may not have the computing power to crunch the numbers on the simulation if it's a virtual thing. Or if it's an experiment, we may not have the computing power to capture, the data acquisition aspect. We may lack the training or expertise. We may lack a descriptive language to model or simulate the thing we're interested in. And time is always the enemy. So anything we can do to minimize the time is helpful. We want to increase our speed because time is one thing that no one has. We're all struggling against time. And that is what takes us into MATLAB. So, So let's talk about MATLAB a little bit. I really like this picture. Makes you think about a different way about the ocean and the surf. I just think it's clever. So what is MATLAB? It stands for Matrix Laboratory. We're not going to get into too much about what a matrix is, but in essence, it's a two-dimensional array of numbers. So if you think about an Excel spreadsheet that's, might be 10 rows by 10 columns, and let's say you put numbers in all of those spaces, that could be a matrix. We'll talk more about it later, though. MATLAB as a product, it's a platform for development, modeling, and simulation. It's an environment that we can work inside of, kind of handles a lot of the details so we can go at higher speed. It's also a language, as in a programming language, a synthetic language, and it's domain specific. And what I mean by that is not that you can't use it for lots of different things, but more that it's optimized for specific things. For MathWorks calls it technical computing, which makes sense. The language is optimized for the expression of vector and matrix operations, and it has a very large library of math functions that are built in. So this makes it very easy to get up and running and start analyzing and modeling and simulating things without spending a lot of time laying groundwork. So when you get into MATLAB, this is a typical screen. I've changed the background colors and some highlighting, syntax colors, just because I spent enough time in there that staring at a white screen is not as relaxing as staring at a gray screen. But generally speaking, your system will look something like this if you have release 2016A. And here are the parts. Number one is the command window, and that's what allows like textual output from your program, or you can actually put in an immediate command if you'd like, and help commands and other things, or full commands. Number two is the editor window, and that's where you can write scripts. It's basically a text editor, but it has syntax highlighting for the MATLAB language. And that allows you to step through it using breakpoints, which we'll talk more about later. Number three, that area is exploring the current folder. You can see above the number three and number two, there's a path that says C, users, Gavin, documents, MATLAB. So these are all the files that are in that folder, and we can open and see statistics and size about those files. Number four is the workspace. And that shows you the currently scoped variables and their information. And so when I say scoped, I mean like the current context. Like if we just opened up MATLAB and I did what you see in the command window, I put in x equals 3, and the interpreter said, okay, yes indeed, x equals 3, then the only thing we've really defined in this context is one variable named x, and it has the value 3. And so you can see that in the workspace there. And then number five, like a lot of applications, it has a command bar with buttons and tabs and ribbons and so on. We'll get into more of that later. So the command window lets us put in pretty much anything we want. We can make declarations, we can put in functions, comments, a full expression, or ask questions. And so let's do that a little bit. It's useful to see it in action. So let's say CLC to clear that up. And let's say 3 times 2. It tells us that's 6. Make this a little bit bigger. I'm going to say clear, which will clear the workspace. You noticed all that stuff disappeared. How about we look at a help file? Let's say help sign. Okay, it says sign of argument in radians. Sign x is the sign of the elements of x. So if we put in sign of pi, it should be 0. This is a numerical. It's not evaluating pi symbolically, it's evaluating a certain approximation of pi, and you can see that the answer is an extremely small number, e to the minus 16. So very, very close to 0. We can also bring up documentation. We could say doc sign, which will bring up documentation window. And here we can read about this a little more well presented. We can talk about can real values, can return complex values, and so on. I'll close this for now. There's a very detailed documentation system. Okay, so that's a little bit about the command window. Now, the next part is the workspace window. And like we've already said, that's showing current variables. We'll talk more in depth about these things, but basically it doesn't update all the time. It updates when things are paused or stopped, or when it has a moment, because it would be taking up unnecessary energy by trying to update that stuff all the time. We'd never be able to read it that fast. So while your program is running, you won't notice those things change, but as soon as your program pauses or stops or terminates, the latest values of the variables will be there in the workspace view. Okay, so now let's hop back here. So we'll start with the language tour, and again, don't panic. It is a new language, but we're just going to cover the stuff we have to today, and we'll do it in little, I said bit size, I mean bite size, actually, chunks. And so we're going to divide it into commands and functions, and there are thousands of commands and functions, but we don't need to talk about them all at once. So you can look them all up in the documentation when you need them, and search for some you don't know the name of. We'll just talk about a few today. Then we'll talk a little bit about operators and syntax, and this is kind of the punctuation. We need to unambiguously say things, and so having proper syntax, proper operators is part of that. There are very few operators, less than 30. We'll just talk about like 10 or so today. Not too many, maybe even less than that. Can't remember. And then finally, reserved words or keywords. And this is the set of the language that you can't customize. Like with the commands and functions, we can write more easily. There are things we can do to create new operators and syntax, but commands and functions are an easy thing to add, and kind of what you'd expect, you generally will add. Reserved words and keywords is not customizable, and they are automatically highlighted. There are very few total. There's only about 20 altogether, but very few of them to use regularly. And today we're only going to use 4. So we just have a few things to introduce here. So here's a few common vocabulary, basically commands that we'll use today. So let's talk about each of these. So the CLC we've already seen, it clears the command window. I'll pull this over here. Oops. Okay. There, that's better. So let's say we said display, this is interesting. So it displays that, and we say Gav equals 87, okay. Okay, so we've said a couple things here. If I issue a command to CLC, that just clears the command window. There's another command here that's listed. It's called clear. Now, that cleared the command window, the CLC did, but you can see the workspace has still got stuff in it. So in order to clear the workspace, which is kind of like wiping the virtual memory in a way, getting rid of any in-context variables and memory variables, we can issue the clear command. So then if we want to issue x equals 4 and gav equals 90, oops, gav equals 90, 909, now we have new ones. Okay. The next we'll talk about this thing called format compact, and that's basically sets the current format. It's very flexible command, format is, but we're just going to use format compact to omit the extra line spaces. Now let me demonstrate. Typically things are in format loose, so when we say x equals 3, we have all these extra line carriage returns, so there's extra lines in there. So when we issue this command to format compact and then say x equals 4, we get rid of all those and it just tightens it up. Makes it easier to read most of the time. Okay, that's good. Then we can issue a plot command. This is the first visualization thing we'll look at. It's very powerful and gives you lots of ways to customize it and see things the way you want to. But it plots a set of numbers on a 2D graph. So I could say plot, and I'll give it a set of numbers, which will give it a set by this square brace, 3, 4, 5, 4, 6, 4, 8, 2. And we'll finish the set, and we'll finish the command, and hit enter. Okay, so it shows us 3, 4, 5, okay, and you'll notice that these are the y values, and the x values are actually the indexes. So the x values used, this is the first index, the second index, the third index, the fourth index. So that's what you'll notice here. This is 1, 2, 3, 4, 5, the little line with the integers there. Okay, I'll close that. Then we have the DISP, and we've already seen this a little bit. So we were playing around in the beginning. What if I say display hello world? I'll run that by I don't want to save it, so I'm going to run it by holding down control and pushing enter. It'll just run the current cell. Talk more about that later. We'll just keep it simple for now. But maybe I have a variable named y, and if I run this, it says it that way. If I want to suppress the output, I put a semicolon there, and then we never see y. Maybe I want to display the value of y without telling you what I'm displaying. Okay, hello world 4. So that's what the display is about. We can output text or numbers or whatever we need to. We've already looked at help and doc a little bit, and there's only 3 more things here. Length. So variables don't have to be scalars. Now let me explain what I mean by that. A variable might be x could be equal to 3, or x could be equal to a set of numbers. So 2, 3, 4, 5. So there's a length command that we have here that returns the number of elements along the largest dimension in a variable. So if I say length of x, the answer is 4. There's 4 elements in its longest dimension. Maybe I make y, and this one is 1, and I put semicolons in here to finish rows. So you'll see what I mean here in a second. So this is stacked up. So we have this would be like a row vector. They're all in a single row, and this would be a column vector. They're all stacked in a single column. So when I ask for the length of y, I'll get the same. It's 4. because each of those are 4 elements long on the longest dimension. Okay, now size is a little more, we're kind of getting more in detail here. So it's going to return the rows and the columns. So we have X and Y, and you remember X had 1 row and 4 columns. So if I ask for the size of X, it'll give me 1 and 4. And if I ask it this way, I can store that answer, the rows in R and the columns in C, and now R is 1 and C is 4. So what if, so that's 1 and 4. Let's see. Size of X is 1 and 4. Now let's look at the size of Y. As we'd expect, it's 4, 1. 4 rows, 1 column. So that's a little bit about, we're talking about the shape of these variables now. And then pause. And pause does exactly what you'd expect it to do. If I want the algorithm to pause for 1 second, that's exactly what it'll do. If I want it to pause for 3 seconds, you can see down here it says busy, and it's just busy pausing. If I want it to pause for 0.01 seconds, we'll hardly notice it, but it did. It paused for a small amount of time. Okay, good. So those are the commands. Now, let's take another step here. How about, we already talked a little bit about this, so I'm going to leave this off. It'll be in the notes, and you can take a look at it later. But we're going to skip it for now, and we're going to move on to common punctuation. So like you've already seen, the percentage symbol is what gets us to be able to comment things. And from a command interpreter point of view, hey interpreter, it just ignores us. But you know, we didn't change our workspace at all. If I clear the workspace, hey, it just ignores. But what's useful though is maybe I have this file is designed to find Gavin's age. He is 3 decades and 6 years old. So I'll say age equals 3 times 10 plus 6. So when I run this, I'm going to hold down Control and press Enter. Age evaluates to 36. But the point is, I put in comments. What was I doing here? What's the purpose of the file? Comments are sometimes hard to get into the habit of putting in, but the more you use your own code and use other people's code, the more you'll realize how important they are. So I encourage you to, even before you start writing code, write the, they call it pseudocode. Write notes of what you're trying to do so you can go back and understand it. Okay, semicolon. Semicolon is used for 2 reasons. One, to suppress the output to the command window. So if I wanted to, let me show you something again. I'll point something out. See how this equals sign, if I hover over it, it says terminate the statement with a semicolon to suppress output. Okay. So it's talking about it almost like it's an error. You may want to output it. In this case, we do. Here, if we put a semicolon after it and we do the Control Enter thing again, we never get to see what age is. Even though it calculated it, we can see it here in the workspace. It didn't output it to the command window. And when you're writing more complex scripts or functions, you don't want to send everything to the window. It becomes confusing. So the semicolon is the way you terminate most statements. The other reason you use semicolons, and we've seen this already with making a column vector, is finishing a column. So one, I want to go, it's almost like a carriage return in a way. So that finishes that row, finishes that row. So I'm kind of making 4 rows here. So it's as if I put the number 1 on one row and then went to the next one, so on. So when I run this, I can see that, okay, y is stacked, 1, 2, 3, 4. And that's how we can, maybe we don't want to put it on the prompt either. Okay. All right, we've already seen assignment. The equal sign lets us assign things. And you may not have thought about this before, but we also need a way to determine equality. So we can assign a value to a variable, but we might want to ask the question, is it equal to something? So if I go back here and I say y equals 3, and then I ask, is y equal to 2, like that, the answer is 0, or false. Does everybody get that? So that's, maybe we don't even want to output it. We don't have to. But we can use this, as we'll see in just a little bit, to ask conditional statements. If this is true, then do something. But we'll get to that in just a little bit. We've already used the brackets. They denote a set. So let's just do that real quickly. Y equals 3, 4, 5, 6. I'll run that. It's a set. 3, 4, 5, and 6. And it ends up being a row vector. I'm finding the parentheses. So they denote parameters in the case of a function. So in other words, sine parentheses 3 sends it. Okay, what's the sine of 3 radians? But now that I have this row vector y, maybe I want to know what the first element. So if I ask what y is, it's 3, 4, 5, and 6. But maybe I want to know what the first element of y is. That's 3. Or the third element of y. That's 5. See? So you can use parentheses to look at subscripted elements. And that's a very useful thing. All right. So, last little bit of language here before we jump in. Do some interesting stuff. We're going to talk about if, while, and else. Not too bad. So if, as you might expect, is just a conditional. If some condition is met, then execute a block of code. So let's do a little quick one here. We'll clean this up. So x equals 3, let's just say, and let's clear the workspace. And if x equals 3, if x equals 2, then let's display x was equal to 2. So we're saying that x is 3, and then we're asking, is x 2? And it's not going to output anything at all because it evaluated that to be false and skipped the block of code. Okay, and I'm going to jump over to, well, let me point out that I used the end block. And when I click on it, it shows me what if this is ending. But we're also going to use the else. So if something is not if something is not true, we can use the else statement to capture x was not equal to 2. So we'll know which one we got to So we'll run this again. And it goes through that and says x was not equal to 2. So we assigned the value 3 to x, and then asked if x was equal to 2. If it was, then we display this, x was equal to 2. Else, we display this, x was not equal to 2. Okay, and I'm going to show you real quickly. This is probably everyone knows how to do this already, but we'll just save this and we'll call it test2. So we'll save the script here, and now we can click the run button once we've saved it, or press F5. Either one will work fine. Alright, so we've used 3 out of 4. Now we want to do the while. Okay, now while is pretty cool because while creates a block of code that loops, and it loops while some condition is met. So how about we do this? Start over, x equals 1, while x is less than 10. We'll end, display x. I'm going to hit run. Wow, we're going crazy. We just keep outputting 1. You can see it's still busy here because x never changes, so this is an infinite loop. Okay, so here's something. We'll put our cursor in the command window, hold down Control and press C, like Charlie, and that's how we can cancel what's going on. Sometimes you need to do that because you've gotten into an infinite loop or something's taking longer than it should. So what if I just say x is equal to x plus 1 and run this? Okay, does this make sense? Now I just incremented x 10 times, it looks like, and I continued to loop. So let me walk through this. In fact, we'll set a breakpoint here and run. Sorry about that. Okay, so you see this little green arrow is where the interpreter is currently evaluating. So it hasn't done it yet. It hasn't run clear yet, so x is still equal to 10. So I'm going to hit step, and it'll take a step down. It just cleared the workspace. Now we're going to evaluate x equal to 1. Or, excuse me, we're going to assign x the value of 1. So we'll say x is equal to 1. And then we're starting this loop. So run this loop while x is less than 10. So I'm going to step. It should display x, which it does. We can see x is still equal to 1. As soon as I run this command, x becomes 2. At the end, it evaluated the while conditional. It's still in the loop, so it continues again. Display. It put the 2 at the command prompt, and the value is still 2. When I hit step, it goes to end, and this continues just like you'd expect, and we can watch in the workspace our value continuing to shift just like we'd expect. Okay, good. So that's a real simple while loop. Alrighty. So the last part we're going to do here is, we already did this while loop. We looked at the editor already. Okay, so let's do a little bit of plotting. We need to learn just a little bit about plotting. So the first one, we'll just put in plot. Okay, so we're going to put in the x values and the y values this time. So that'll be the x values will be 1 and 5, and that'll be paired up with the y values of 4 and 11. Okay, so I'm going to run this. Okay, 1 and 5, 4 and 11. Plotted a straight line, just like we expected it to. So 1, 4, and 5, 11 were the two coordinates that got plotted here. Alright, so that's a simple plot. Let's close that plot window. Now, what if we use some variables to do this, though? Okay, what if we say, we'll use our while command, and we'll say x equals 1, while x is less than 10, and y equals x squared. And we'll suppress the output. Okay, now we're going to do let's see, what will be the easiest way for you to see this? Let's actually do it like this. Plot x and y, pause for half a second. Okay? Now we're going to run this. Okay, and we actually have an issue here. It's busy. We totally forgot to increment x. We need to say x equals x plus 1. Okay, so when I do this, it's going to create the plot here, and we can see that it's moving up, but we can't actually see the dot, right? So we're going to change a little bit about the plot and just say, make it a dot. That's by putting in this period. Now let's rerun that real quick. Okay, and it keeps centering it each time. Not super exciting. Okay, now I'm going to do something interesting. I'm going to make something called the list, list, and it'll be equal to 0, and the y list, it'll also be equal to 0. Now, I'm going to make this, I'm going to extract the y and x so that the x list uses itself and then the new x, so we're going to append it to the end. Sorry, there we go. And then y list equals y list and y. Now we're going to put the dot, and we'll add the line segment as well. So let's run this again. This should be a little more interesting to look at. We're iteratively adding those dots. Pretty cool. Okay, very good. So now, close this plot window. Okay, this is same kind of thing. I think we'll skip this one for now. And this is just evaluating the sine function, but same idea as what we had here. This just evaluated the square function, but we could have said it was the sine of x. Well, we'll just do it for the heck of it. Sine x, and we'll let this go to 20. Let's see what this looks like. Interesting. There's our sine function. Maybe we should try... Oh, we squared it. That's why that was a little bit weird. Let's put x over 3, just so we have a little bit better fidelity. We'll close this. That's cool looking. Alright. Good. And the last thing, well, we're going to add a few different commands just to give ourselves some vocabulary so we can make these things look nice. And we'll add a grid, and we'll be able to set the limits, both in x and y. Turning hold on and off allows you to put more than one thing on top of itself, on top of, so like you could plot one variable and then plot another variable on top of it. X label and Y label is just like you'd expect. It just lets you label the axis, and that's so that we can kind of make things look right, and when we don't have to go back to the code and figure out what was what. And then finally, plotting parameters, and this will be things like line color, line size, line type, marker color, line marker size, marker type. So for example, we can change our color in this, and we'll just do this one, marker XY, and then we add this, the third parameter is color, and the value we're going to pass it is R. So let's do that real quickly. Go back to MATLAB. Color R, and that'll make it red. So we can customize the plots and kind of get things the way we want them to be. All right. So we'll use a few more of these things. How about X, add an X label, and this will be, let's call it time, and a Y label, and we'll call it RY output. If I run this, you can see, actually I spelled it wrong. I said Y output. That's okay though. You get the idea. And I'll make this 0.2 so this goes a little bit faster. We were going to add a grid and the limits. Okay, so say grid on. Okay, makes it a little easier to see sometimes, adding that grid. And the limits. So maybe we don't want to be stretching. Did you notice how this stretched the whole time? Kept stretching on it. Maybe that's not quite the effect we want. So let's add xlim. We have to do this as a set. So 0 to 20. That way it won't stretch at all. And then I don't want it to stretch in y either. So I'm going to put ylim for y limit from -1 to 1. Okay. So when I hit go, now that holds still and I can kind of see what's going on. Perfect. Alright. So that's about it for the language stuff. Now it's time to, well, we'll learn about the hold during the thing. Let's get some. let's get our first blood here. Okay, so the challenge is to design a bouncing ball simulation, and we can do this with the stuff we learned today. So we want the ball to bounce between two borders, 20 inches apart, centered on the origin. Okay. So by ball, I mean dot. We also need to make a visualization of that so we can see what's happening with the ball in real time. And then if time allows, we'll elaborate this and we can add all kinds of cool stuff. So how do we go about this? We first need to create a new script. We need to create a variable to store the position of the ball. So let's go get dirty. I'm going to close this. Close this. And this one too. Okay, here's a new script. Most scripts that are kind of self-contained that you're going to run as sort of a master script, we want to start with this. Clear, format compact, CLC. Clear clears the command window. We'll add some comments here. Clear the command window. Oops, sorry. Clear the workspace. Actually, you know what? Just to keep this nice and compact, we'll put it like this. Make the output compact. Clear the command window. I guess we haven't talked about how you can put comments after a command as well. It'll be ignored by the interpreter. Alright, so we want to model a bouncing ball. How to do that? Like I said, first thing we need to do is we need variables to store the position of the ball. And we really only need one, so I'm going to call that the position of the ball, position X. And I'm going to start it at 0. Okay? Alright, I'm going to make this window a little bit smaller so it's easier to see. Alright. Let's visualize. Okay, so we're going to use the plot command to visualize. Plot position X. We'll put it at 0 on the y-axis. And we want to use a dot. We know that. And I'm going to add another thing that we didn't talk about explicitly, but I'm going to add a marker size equal to 30. So that'll give us a good sized dot. Alright, so if I run this, oh, that's right, let's call it project 1B. Okay. So at 0, 0, we just put a dot right there. And that's fine. I'm going to add a grid, so I'm going to turn the grid on rather. So I'll hit run again. Okay, so we have a stationary ball. That's a start. But we got to move the ball. Okay, so we kind of need to introduce time or some movement of some kind, right? So let's add how much we move. Well, actually, before we do that, why don't we loop here? We'll add it right here and say while something, I'm not sure yet, it's going to complain at me about that, end. Okay, highlight this and press the Tab key to shift it over. Okay, so I want to run this thing, but how do I know when to stop? So for the moment, I don't want it to stop. I just want it to keep going. So I need a condition that's always true. So that condition, I'm going to say while 1 is equal to 1. Just for kicks. Okay. Now, if I hit go, it says I'm busy. It doesn't look like it's updating. It's hard to tell though since we're not moving. But one thing I do notice is that we didn't pause. So I'm going to pause just half a second. Try running that again. Okay. Yeah, it didn't update before because it didn't turn the grid on, I don't think. Okay. But again, it's not moving. So now we have something working here, but we need to add movement. So we'll call it move step. Move distance equals, how about 1, just to start with. Okay. So we'll say the position x equals whatever the current position x is plus move distance. So it's going to keep taking a little move forward every time. Okay. I'll click once there, click on run. Alright. Okay, we can see that this is working because you can see the numbers going by. It's kind of like looking at watching a plane through a spyglass. You don't have any context and you just notice this number is changing. It doesn't really look like the ball's moving. So it's doing something. It's not bouncing yet, but let's use the xlim commands so that we can kind of think about this better. So let's turn xlim. So we know that we want to go from, I think it was -10 to 10. Actually, I'm going to make that -20 to 20. -20 to 20. I just decided to make this with bigger space. Okay. So if I run this, click on the editor and run. Okay, I have a moving ball here. And as you guessed, we have an issue because there's no bounce. Okay. So how do we get this thing to bounce? That's kind of the question here. Well, what happens in a bounce? Well, let's kill this first. What happens in a bounce? So there's a collision, right? Collision. So the collision depends on the position x getting past 20. So we'll make a conditional statement here. Use the if position x is greater than 20 and we want to turn around. Go to the left. Okay. So we could say we have a move distance, and the move distance is 1, so we could make move distance equal to -1. Then when we get to 20, it'll automatically automatically turn move distance to -1, and then it'll go backwards, and I think that should work. Okay, let's try it. So the little ball gets out there. Whew, okay, it bounced. And now we're all thinking maybe we should have this go faster. I'm agreeing with that thought. But I want to take a second and see the fact that it's not going to bounce off the left side, because it isn't there anymore. There's nothing to catch it. So let's add another one. If position x is less than -20, and that block, turn around to the right. Move distance equals 1 again. Alright, so let's, we'll just go 1/10 of a second now. It should move a little faster. Well, that's cool. That didn't take too much. Okay, so now we have a bouncing ball. But something weird is happening. We're losing sight of it, right? It's like it goes off the edge. And you might have guessed why that's happening. That's happening because the ball has to be greater than 20. Let's look over here. The ball has to be greater than 20. So that means we want it to bounce off of 20, but in order for the simulation to understand that the collision has already happened, it has to be greater, because equal to 20, you probably won't hit that exactly, and less than 20, we don't want it to collide at all. So how do we deal with this? Okay, well, we have a little model here that's working. We're simulating it, and we can see that it's working. It just has a little quirk. So what we need to do is add a little way to track. Basically reconstruct what happened. If something's happening, we know that it's going past 20, but we need to understand this better. Okay, so let's look. We'll hit Control-C here in the command window and stop it. Alright, so I'm going to do something kind of interesting. I'm going to say I'm going to call this the path in x. I'll set equal to 0. So I'm initializing a variable here. At the bottom, I'm going to say that the path x, so the path where it's been, is equal to whatever the path of x was, and then we're going to add the current position x as another column. So it's going to keep pending the path to itself. And I'm going to turn this up just a little bit more, just so it doesn't take quite so long. So it's going to be 50 millisecond sample time here. If I run this, ding, ding, okay. So that should be enough. We're capturing some good data here. I'll hit cancel. Alright, let's take a look at the workspace here. Path X has 1 row and 171 columns. So that means we captured 171 data points. Now, I'm going to introduce a new command here called figure. It'll just open up a new figure. And I'm going to plot path x. Okay. So this is kind of what we expect, right? We increment, actually I'd like to see the dots too, so I'm going to try that again. Plot path x and use a dot. Actually, we'll use an asterisk and then put the line after it. Okay. We kind of have these fuzzy things. Change my mind again. I'm going to use a dot. Asterisks are too fuzzy. Okay. Alright. Now, let's take a look at this thing. So, actually, I want to turn the grid on. So I'm using the command window here because I don't want to simulate this stuff again. I don't want to run the whole script. I want to analyze what happened. Alright, so I'm going to zoom in here on the first turnaround. And I can see here's 20. It actually landed right on 20, it looks like. We have we can add data tips here if we like. Yep, y is 20. And then it went up to 21, and then we told it to turn around, so it came back and did this. What should it have really done, though? It really should have come back. So let's make our sample time a little different so that we don't end up right on 20. Okay, I'm going to close this. Actually, what I want to do is make our move distance slightly different. 0.03. 2.3. Alright, that's better. Okay. So, let's run this. It's a little bit faster. Bam, bam, bam. We got those. Perfect. Alright. Clear command prompt window. Create a new figure. Plot. Remember, we're going to put it on the current figure here. Plot. Remember, we made this path x. Path x to analyze this again. Using dots and lines. Good. Turn the grid on. I'm just going to add a y label. This is actually the x position. And I'll add an x label. This is the variables index. Alright. So let's have a look at this. Interesting. You recall, we only made it this in the beginning, and then at our 2, we turned it back to -1 and 1. So we made it 2.3, and then it went back to -1 and 1. So that is doing what we told it to do. Let's just zoom in here, though. I want to look at this collision. Okay. So it took this step from here, 18.4, and the next one was 20.7, in which case it turned around. Right? So what I want to do is basically I want to talk about what should have happened. It should have gotten to here and then bounced, right? But the problem we have is that we're simulating this reaction at a fixed time step, and the time step doesn't exactly line up with the collision, right? Because at this time step, we're here. The next simulation time step, we're there. And then we know we should have turned around. So we detected the condition after it took place because we couldn't detect it before. And we couldn't change our solve times to line up exactly. So what we want to do actually is look at, we're going to wait till after it happens, but we know that what should have happened was we bounced off of 20, and so we should end up over here, okay? So if you think about this, we went 0.7 past 20. So at this same point in time, we actually should be 0.7 below 20 because it should have bounced right here, right? Should have bounced here, and we should be at whatever that is, 19.3 at that point. So it should be the mirror down there. So really, all we have to do is add in, sometimes this is called a restitution. We're restoring this to where it ought to be. So we're going to call this dx. Let's figure out, okay, when it's past 20, dx is, dx is our delta x, our amount too far. We'll say dx is 20, actually, we know it's too far, so it's position x minus 20. And that's how we went too far there. And so we want the new position x to be position x, and we're dx too far, and we should have gone the other direction. So we really need to be 2 times dx lower. So we'll take our current position and say subtract 2 times dx. Okay. For this, it's the same idea. It's just that some of the signs are a little bit different. So let's look here. Just so that we can zoom in, we can think about it a little bit. dx equals we know we want dx to be positive so that we can think about it easily, and so the larger we're going to go past, so it's going to be more negative, and so position x it's going to be 20 minus a negative number. Well, why don't we do it the same way? It's actually going to be negative if we do it like this. But we will add absolute value just to make sure it's positive. Okay. And then we'll say position of x is equal to the position of x. And this time we want to make it higher. So we want to add. We were here. This is where we actually hit. We want to bounce to be up here. So we've got to go dx to get back, and then 2 times dx to get where we're supposed to be. But we have to add it again. 2 times dx. That makes sense? All right. Good. Well, let's test this out. See if it works. Let's hit Control C and figure out what happened. Position X is 233, and DX is really big. Okay. So we know it's over here. The issue is over here because it didn't bounce right. Alright, so we should have bounced. So I'm going to put a breakpoint right there. And hit play. Okay, now it's just about to tell us what's going on. It hasn't plotted it yet because it's moving. It's the next move. We can hover over this and see it's 20.7. Okay, so 20.7 and dx is, like you'd expect, 0.7. So when we take one step further, the new value is 19.3. Good, that's what we expect. So we'll continue. Okay. Now it says our new position is 61. That's not very good. So it must have happened here in the position X at the negative collisions. So let's look at this again. So, I see what we did. See, position X is less than negative 20, and so we took negative 20 and subtracted 20 more. So, let's add 20. And that should get us where we want to go. So we need to kill this. I have to quit debugging first. Clear the command prompt. Let's run this. That looks better. Now the dot never gets off. Okay, let's take a look at path X just to be sure this is doing what we expect it to be doing. We'll add a new figure. Plot path X with a dot and using the line, turning the grid on. Alright, let's take a look here. So let's look at the first one. So if we use a line, if we draw a new line here, and that means we should have collided right there, more or less, right? Okay. I'm going to insert another line and see if our path that's interesting. Not quite at 20. The idea should have been that this might be just not lining ourselves up very well here. I'll try to get these lined up a little bit better. About 19.7. So we're a little bit off, but we are staying inside of 20, which is our intent. So we're close. We're close. A good example of not having perfect accuracy. I think for the moment we'll go with it though. Let's take a look. I'm just curious. if the other side, we have to get rid of these lines that are sticking around here. Just clicking on the line and pressing delete. Let's take a look at some of these other ones. Maybe this one down here. Because of the fact that we changed our speed right after the collision, that might have been what threw us off. So let's look at that. Line. We'll draw a line here. That looks pretty good. Insert a line. Much better. So the algorithm is right. We changed speeds and right at the collision. So what we're looking at. So now you can see that it did actually collide, but we skipped that frame of time. Well, we didn't skip it. It happened between steps. So we're plotting all the positions that we actually simulated, and that one we detected and skipped over. So that's exactly what we wanted. Very good. Pat myself on the back there. Okay. So now the next thing that we want to do is kind of add a formal notion of time, because right now we're just looping. So we can't set a real speed. We have this little, what do you call it, move distance, but we shift it around all the time. So we need to do a couple little things so that we add a good notion of time. So I'm going to add something called, I'm just going to add a variable called time, or t rather, and I'm going to add a variable called step. And so the step, well, this is going to be our time step, and we'll just call it we'll make it film speed, but 24 frames a second. Okay, so why is this useful? Well, first of all, we can track exactly how much time has gone by. We set t equal to 0 initially, and then at the end of this thing, we'll say t equals t plus step. So it'll update on every loop, and it'll get bigger and bigger and bigger. Okay. So that's our current time. We can also get rid of this 0.05 and just say pause for whatever the step time is. Then this actually becomes real time. Okay, that makes sense. So just before we change too much, let's run this and make sure everything still works. Bing, bing. Okay, everything's looking good. I forgot. Got to cancel it down here. Okay. All right. Now the other thing, instead of having a move distance, we may as well just make this a speed. But we need to talk about that for just a moment and talk about why this works out. So we started doing our demo. So let's think about using velocity to calculate position. So one way to look at this is our position has, I'm just going to say, has units of inches. They're purely numbers at the moment, but let's just assume that that unit is inches. So we'll assume our velocity has units of inches per second. So now that we have some measure of time, we can multiply by that step of time in order to see how big a step we took as far as position goes. So think about, you're driving in a car, and the step time is 1 hour, and I'm in Chico. Step time is 1 hour, and I'm headed north. Well, it doesn't even matter what direction. 1 hour, and I'm going 60 miles an hour. So how far did I go? I went 60. How did we do that? we multiplied velocity times the time step. If I'm going 60 miles an hour and I drove for half an hour, then I should have gone 30 miles. Velocity times the time step. So let's go back and add this in. Let's add this back into our simulation. So I'm going to call this velocity x equals 3. Okay. So right now we change the move distance, right? We're going to change that. Instead of the new position being calculated based on the move distance, it's going to be on the velocity of x times the step, right? Okay, but that means that at each collision, we also need to do something different. And really, we just have to reverse the velocity. That makes sense, right? So velocity of x is equal to the negative velocity of x. And we can do exactly the same thing here. Velocity of x equals the negative velocity of x. So if you're already negative, it makes you positive. If you're already positive, it makes you negative. And that should work pretty good. Let's try it. Boy, that's slow, huh? I don't think I have enough patience for 2 collisions, but okay, 1 collision. Nice and smooth, though. It's starting to actually look almost physical. Okay. So I would like to speed this up, so I'm going to increase my velocity to 15. Run. Okay. Good. All right. Now, I also want to be able to change my time step without affecting the speed. But this should be just fine. If you think about it, our velocity is independent of our step now. So I want to try changing this. Instead of being 1/24th, I'm going to make it 1/100th. So let's try this. We'll run it. About the same speed. That's perfect. But because our step time is now 1/100th of a second, now our path x has gathered 575 points. Remember, we are appending to the end of path x. So we went for about 5 seconds, and it's getting about 100 a second. So that makes pretty good sense. All right, so that's pretty good. I'm going to go back to 1/24th because really don't need to go much faster than that. Alrighty, let's see what else to do. Getting a little bit low on time. We've got about 10 minutes left here. So I would kind of like to see how we could do this in 2D. I think that would be pretty cool. Now, I'm going to just add a slide about this. The method of components, we could talk about the angle of the bounce, and we could talk about, the aligned velocity, but we've already solved the problem in 1 dimension, and so really we just need to make a copy of the same solution and combine it. And I'll show you how we can do that. So basically we're solving 2 problems at the same time, and then we can plot both the x and y coordinates of what's going on. So let's implement that. This is actually a pretty fun part. Okay, so for every x we need a y. So make a position y equal to 0. And we'll make a velocity y equal to, how about 5? How about 25? Okay. We'll make a path y equal to 0. Okay. So now we're not going to be plotting position x and 0 y coordinate. We're going to be plotting the y coordinate. And we'll also need to limit the x's from minus 20 to 20. And that's correct. We need to update the y position the same way we updated the x position times the step. Okay. Alrighty. So let's add if position y is greater than 20. So we know velocity y is going to equal the negative velocity y. Dy is going to equal to position y. I'm just copying this from right above. And position y equals the old position y minus 2 times dy. Okay. And we need to make another boundary for y if it goes to negative 20. So if position y is less than negative 20, then velocity y equals negative velocity y. Dy equals the absolute value of position of y plus 20. Position of y is the part where we do the restoration. Remember the restitution. Position of y plus 2 times dx. Oops, dy. Alrighty. And you would think it would be harder, but that's about it. Well, let's see if that actually makes sense. You know what we forgot? We forgot the limit. We forgot to set our limit for, we set 2 x limits. There, that should do it. We changed it from x lim to y lim. So we have 1 x lim and 1 y lim. We have a 2-dimensional bouncing ball simulator here. That's pretty cool. And something else that's kind of cool. Now that we have 2 dimensions, we can actually trace where it's been. So then we can try using the hold command. So how about, because we know that we have path x, we need to add a path y, don't we? Path y equals, we already initiated or initialized it up there. So we'll use the old path y plus position y, append that to the end. And then, this is kind of cool. Alright, so I would like to plot the path first and the dot on top of it. So first we'll say hold is off. So you don't keep going on top of something. It's going to be like a new plot now. Plot path x, path y. And then we'll hold on, and on top of that, we'll put this stuff. Okay? Aha! Pretty cool. that's kind of interesting. It bounced exactly. It's almost mesmerizing. Well, wouldn't have guessed that I would have such symmetry here. That's okay. Alright. So, I want to add just one more element. We've got a couple more minutes. This is cool, but what if we add gravity? Gravity's kind of fun. So let's just talk about gravity for a second. We can even let this run while we're looking at gravity. The angle of incidence was already taken care of, so you can look at this to be sure that the math lines up, but we actually took care of it just by reversing angles. That's what this slide is talking about. So we already made it 2D, and we demoed it. So if we add gravity, we're really just bending this a little bit. We want to be able to bend. And how do we deal with this? We've all taken those kind of tests that say a question like, Peter is to Pan as Mickey is to, and is it Hook, Mouse, Piper, or Flute? Okay, well, Peter Pan is the name, Peter is the first name, Pan is the last name, and Mickey Mouse is, so the answer is B. So altogether, the answer is B. Well, as it turns out, velocity is to position as acceleration is to velocity. Because of the fact they're both rates of change, velocity is the rate of change of position, which we saw we can just multiply by the step to change position. Acceleration is just the rate of change of velocity, so we can do exactly the same thing. So let's hop back in there and add, this is still running actually, and it can run while we make the change. That's useful to know when it's running and you make a change and even save a change. It's not running what you saved, it's running what you ran. So it kind of has a, it's not automatically updating based on your latest change until you stop it and rerun it. So I'm going to add gravity. And gravity is going to be equal to, we're going to have it pull down, so it's going to be -5. Actually, I'll make it -10. We can always adjust it. So let's go to the place where we adjust the positions. Alright. Now, we're not going to affect the x velocity, right? Because we're just pulling down with gravity. So we'll say velocity y equals the old velocity y plus, now where we would have said something about velocity y times step, we're going to actually put gravity times step. Okay. And believe it or not, that's actually all we need. So let's run this and see if this looks interesting. Oops. It says we don't have gravity. Did I spell it wrong? Yes, I did. There it is. So you can see that was the issue, and now we fixed it. We added an R to gravity. Let's try running it. Now we've got a little bend. This is getting a little bit more interesting. Okay, just for kicks, let's turn up gravity a little bit, right? What's the point of doing simulation if we can't play with it? Let's turn it up to 20. So now we're going from Earth to Jupiter or something. You can feel more gravity here. Very cool. Alrighty. Well, this has been fun, and I think it's a good time to stop. We've introduced MATLAB, and we've made an interesting bouncing ball with gravity simulation, and we've shown how we introduced a simple model. We didn't try to do any crazy math. We just had little if statements for those collisions, and we introduced a time step, and so that's the step that the solution's taking, and it's simulating in real time. We introduced gravity, and we actually introduced some interesting analysis points, right? Because we looked at how we could analyze this in time and analyze it in space, and with this little path X. And then we visualized this all together. So I think we made a good amount of progress today, and hope you can join us the next time or see the video. Thanks.